While studying principles of flight, for simplicity, we assume that air is incompressible, but this is only valid for low-speed flight. For high-speed flight, we must consider changes in air density due to the changes in air pressure. This is known as compressible flow. When an aircraft moves through the air, pressure waves are generated. To generate some pressure waves, we're going to hit the nose of a stationary aircraft with a hammer, but in flight it will be particles of air that generate the pressure waves. The vibrations from the blow generate a series of pressure waves that move outwards through the air from where the hammer hit the aircraft, the point source. If we zoom out a bit, we can see what is going on more clearly, and for clarity, we'll show just one pressure wave. The pressure wave propagated from its point source, and then the picture was frozen. In the time between the pressure wave being generated and freezing the picture, the pressure wave moved through the air at a certain speed. The speed of pressure wave propagation is called the local speed of sound, represented by lowercase a. The only thing that will affect the speed of sound is the outside air temperature. The higher the temperature, the higher the speed of sound. In the same time interval, but with a higher temperature, the pressure wave would have propagated further, but not so far at a lower temperature. At a constant outside air temperature, do you think the pressure wave will look the same if the aircraft is moving when the pressure wave is generated? Of course it will. Nothing has changed. The pressure wave was generated in the same place, and the air temperature was the same. So the pressure wave will travel the same distance through the air in the same time. But in the time it took for the pressure wave to propagate, the aircraft will have moved forward from the point source of the pressure wave. The pressure wave moved through the air at the local speed of sound, and the aircraft moved through the air at its true airspeed. To understand the relationship between the local speed of sound and the aircraft true airspeed, we need to remind ourselves of a fixed reference point, the relative airflow. True airspeed is the speed of the aircraft through the air. But which air? The air just in front of the leading pressure wave. The trailing pressure wave is included for reference purposes only. During the study of high-speed flight, the most important aspect of the relative airflow is that it is close to, but as yet unaffected by, the presence of the aircraft. For general review, the relative airflow is also parallel to, and in the opposite direction to, the aircraft flight path, and the length of the vector represents the true airspeed of the aircraft. As soon as the pressure wave passes over an air particle, it is no longer relative airflow. It becomes effective airflow. More about this in a minute. Throughout our study of high-speed flight, there are two major characteristics in which we are interested. The one we will illustrate now is the proximity of the aircraft to the leading pressure wave. The second characteristic is the formation of shock waves, which we will look at later. There is a ratio between the aircraft true airspeed and the local speed of sound. This ratio is called the Mach number, usually shortened to m. The true airspeed of the aircraft in this illustration is 264 knots, and the local speed of sound is 660 knots at 15 degrees C. The Mach number is therefore 0.4. This is said as Mach 0.4. It is important to remember that both the speed of the aircraft and the speed of the pressure wave use the relative airflow as the reference air through which they are moving. We learned earlier that relative airflow can also be called free stream flow. So the Mach number we are discussing here is called the free stream Mach number. The free stream Mach number is basically what is presented on the aircraft Mach meter. The scale shows the aircraft at 4/10 the distance from the point source to the leading pressure wave. But this fact doesn't help us understand how high-speed flight affects the aircraft. It is this that will have an effect on the aircraft. How close the aircraft is to the leading pressure wave. We can now examine how the pressure wave changes the airflow approaching the aircraft. As soon as the pressure wave passes over an air particle, it is no longer relative airflow. It becomes effective airflow. The leading pressure wave effectively acts as a messenger. It tells the air, "Here comes an aeroplane, you'd better get out of the way." You can see that as soon as the pressure wave passes over the air, it starts to upwash. The higher the Mach number, the closer the aircraft is to the leading pressure wave, and consequently, the air has to upwash through a greater angle. You learned during your study of stalling that this will cause CL max to decrease. Hence, stall speed will increase. The effect of this change will be discussed in detail later. Anything that is moving will have a Mach number. A person walking will be travelling at Mach 0.005, firmly in the low-speed flight region, where we don't need to worry about how close we are to the leading pressure wave. A training plane cruises at about Mach 0.14, a light twin at Mach 0.3, and a turboprop commuter aircraft at Mach 0.4. All these examples operate at speeds less than Mach 0.4, when their proximity to the leading pressure wave has no significance. It is only aircraft that operate above Mach 0.4 that need to know their proximity to the leading pressure wave, and consequently will be fitted with a Mach meter to tell the flight crew the aircraft Mach number. We'll now consider something called the critical Mach number. The critical Mach number is not used operationally, but is an important reference for your understanding of high-speed flight and your ability to answer exam questions. Here is a view of the wing, with the airflow accelerating over the top surface. The airflow will reach maximum velocity relative to the wing surface at the point of minimum cross-sectional area of the airflow. The maximum velocity of air on the wing will always be faster than the true airspeed. Otherwise, there would be no lift generated. The maximum velocity of air on the wing is called local velocity, because we are discussing air relative to the aeroplane surface. We can now introduce a Mach number called the local Mach number. The local Mach number is the ratio between the speed of the local velocity over the surface and the local speed of sound. Remember, the local Mach number will always be higher than the free stream Mach number. In this example, the free stream Mach number is Mach 0.55, and the local Mach number is higher at Mach 0.8. Let's see what happens as the aircraft accelerates in level flight. Both the free stream Mach number and the local Mach number are increasing. Notice the local Mach number has now reached the same value as the speed of sound, Mach 1. Bear in mind that the free stream Mach number is effectively the aircraft Mach number you'll be seeing on your Mach meter. The aircraft Mach number, at which the local velocity first reaches Mach 1, is called the critical Mach number. The critical Mach number is usually shortened to m-crit. The reason that m-crit is such an important reference is that as soon as m-crit is exceeded by even the smallest margin, a shock wave will start to form at the point of maximum local velocity. In the next lesson, we will examine why shock waves form, and later we'll look at their effect on the operation of aircraft during high-speed flight.